All right, hello everyone. So in this lecture, we're going to talk about periodic trends. And these are trends in certain properties that we can figure out just by looking at the periodic table, okay? So a really good one to start off with is this idea of atomic size or atomic radius, basically how big each one of these atoms are. If I were holding a magnesium atom in my hand, how would that be compared to, say, a helium atom in size? And this is a really good one to start off with because it's both intuitive and counterintuitive, right? So if I were to select, say, hydrogen versus, anything down here, I don't know, what is that even? Rhenium. Which one do you think would be larger in terms of the atomic radius? Right? So you probably would assume because hydrogen has so few protons, it's quite small compared to rhenium, which is number 75, so it has 75 protons, is quite a bit larger. And that is indeed one of our periodic trends, is that atomic size increases as we go down the periodic table, right? So hydrogen is smaller than lithium, is smaller than sodium, is smaller than potassium, et cetera, et cetera, et cetera, okay? But this is also a pretty cool one to see because the other direction is a little bit counterintuitive. So let's see this list of periodic trends right here. Notice that this is just the periodic table, but I've cut out from right here the transition metals, right? So notice this is beryllium and boron. This is beryllium. This is boron. So I've kind of cut out this middle chunk here. This trend works even within that. I mean, truthfully, they tend to stay the same size. Doesn't really matter. The only reason they do that is to exaggerate the periodic trend here. But again, let's sort of take a look. Ooh. Notice how as I'm going across, right? So lithium has an atomic number of 3. Beryllium has an atomic number of 4. Boron has an atomic number of 5. Carbon 6. Nitrogen 7. Oxygen 8. Fluorine 9. Neon 10. Notice how I'm actually getting smaller as I'm going from left to right, okay? This is kind of counterintuitive because we're adding more protons and yet our actual atomic size is getting smaller. I'll explain why that is here in a second. But more importantly, I just want to note that this is indeed the trends of atomic radius. They get larger going down the period, but then they get larger going from right to left, right? So the one makes sense, the one way makes sense. The other way is a little counterintuitive. And we can discuss why that is. It actually has a lot to do with the Bohr model of an atom. If we think about it, a lithium atom, okay, let me actually include these 4 or 5. A lithium atom has an atomic number of 3, so that means there are 3 protons in a lithium atom. And it has 3 electrons, 2 of which are core electrons, and then 1 on the outside. Okay. Actually, next lecture, we'll talk about those very outermost electrons are called valence electrons. Now let's go over to fluorine or something like that, something on the other end of it. It has 9 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 electrons. But 7 of those electrons are sitting at the same principal quantum number, right? So this innermost electrons, these would be a principal quantum number of 2. Those outer electrons would be a principal quantum, innermost electrons would be a principal quantum number of 1. The outermost electrons would be a principal quantum number of 2. Remember, these are lithium would, or rather, fluorine would be 1s2, 2s2, 2p5, whereas lithium would be 1s2, 2s1, right? So this is its n equals 1 layer and its n equals 2 layer. Okay. Oh, I didn't draw these to scale. That's my bad. I was kind of trying to exaggerate a point here. The bottom line is because though all those electrons are added to the same layer, and notice what happens to this, the size of my nucleus in terms of the number of protons, right? So lithium has 3 protons that are pulling in all those electrons. Fluorine has 9 protons that are pulling in all those electrons. And although there are 9 electrons, 7 of them are sitting at that same level. So it's able to pull them in that much easier. Okay. So the fact that, you know, we are adding more electrons, but also that the size of our nucleus in terms of the number of protons and its ability to pull in those electrons is also getting stronger. So bottom line is increasing atomic radius will occur from right to left. So things on the right side of the periodic table are smaller than things on the left side of the periodic table. So this is our, if we're going to like look at our periodic table, these are the trends that I'm talking about. And again, this is for atomic radius. And so this right here is the skill that you're going to need to be able to answer problems from this chapter. Basically, you want to be able to look at a periodic table. We'll get rid of all these little markings. And for a particular periodic trend, and again, in this case, we're going to say atomic size, you want to be able to draw arrows that say, I know it's getting bigger this way and getting bigger that way. Okay, because what I'm going to do is I'm going to say this one or this one, which is bigger, right? So you're going to have to know that trend. Likewise, I can say this one or this one, which is bigger, right? So being able to look at your periodic table and know the direction of those trends is the important skill that we need here. Okay, so let's do an example. Which one of these elements are bigger, aluminum or phosphorus? And again, you can note that like I'm really good at knowing what my symbols are. You guys might have to hunt around the periodic table a little bit more. That's just something that's going to happen at the beginning of the course that you'll get better at. So aluminum and phosphorus. Here's aluminum, here's phosphorus. So which one is larger? Remember, my atomic size increase is going towards the left. So that means that aluminum is the larger of the two. What about selenium and oxygen? Again, I'm going to just find on my periodic table where is selenium and where is oxygen. And I'm going to note that things get bigger going down the periodic table. So selenium is the larger. Okay? So there are a few. This atomic size is kind of the easiest to wrap your head around because you can imagine atoms as little marbles and they're different sizes. The other two that we're going to talk about are a little bit more abstract, or not abstract, but a little bit harder to wrap your head around, but bear with me here. So the first one is called ionization energy. Ionization energy is the energy required to remove an electron. And in particular, we'll talk about the first ionization energy, which is the energy required to remove the first electron from a neutral atom. Okay, let's look at the trends here. We can tell that it's the easiest to remove are at the bottom left of the table. The hardest to remove are at the top right of the table, right? So our trend is kind of pointed this way. All right. I will say everything, it's not sort of all created equally. Everything over here has a pretty high ionization energy compared to everything over here, okay? So the dominant trend is this way is easier to remove. All right. And then it does once, sort of once you got that, it is noteworthy that, rubidium, it's easier to remove an electron than sodium. But I'll say everything on that left half of the periodic table will very readily give up an electron. This is something that we'll talk about next lecture when we talk about ion formation. But anyways, yeah, so again, the whole idea is we're going to grab a periodic table and we're going to be able to draw these trend lines in. And then if I say, which is easier to remove an electron from, phosphorus or chlorine, you'll know that it trends this way. Phosphorus is easier, okay? So let's go ahead and draw those in. What's going on there? It's easier to remove going down, going this way. So notice it's actually the same trends as the atomic radius trends, so that's nice. Ionization. All right. So now let's do some practice problems here. If I want to choose iodine or fluorine, which one's going to have a higher ionization energy, meaning which one's going to be easier, or which one's going to have a lower ionization energy, sorry, is the problem. Low ionization energy equals easy to remove an electron. Right, ionization energy is the energy you have to put in to pluck an electron off, right? These electrons are in this atom. If you want to reach in and grab one and pull it off, it requires energy. So what was it, iodine and fluorine? Yes. So here's fluorine, here's iodine. Which one's going to be easier to remove an electron from? Turns out that it's iodine. And what about lithium or rubidium? Again, we can see the trend going down. It would be rubidium. Okay. So why does it trend this way? So first of all, we'll see that there's a big difference between this half of the periodic table and this half of the periodic table in terms of the type of ions it likes to form, right? Because let's say that I'm lithium, and then I'm going to lose an electron. Originally, I start off with 3 protons and 3 electrons. If I lose an electron, I go to 3 protons and 2 electrons. So what would be my net charge? This would be +1. It turns out that everything over on the left side likes to form positively charged ions, so they give up electrons pretty easily. Everything over on the right side likes to form negatively charged ions, so they accept electrons easily. Okay, so the left to right, or rather the right to left trend of decreasing ionization energy, or rather easiness to remove an electron, is pretty easy to understand in terms of the types of ions elements like to form. What's a little bit harder to understand is the top to bottom trend, okay? And that simply has to do with the fact that if I am, for example, something very tiny like a hydrogen, where I have 1 proton and 1 electron, versus, let's just make my life easier in terms of drawing, but a sodium, which has 11 protons, but it also has 3 different principal quantum number. Whoops, there should be a 1, n equals 2, n equals 3. So by the end of it, even though these both have one electron out in that last shell, sodium's electron is way further away from the nucleus. So it's a little bit easier to be picked off. So that's why, so this downward trend is actually more of a trend in size. And I guess, let me be clear here. This is actually ease of electron removal. In terms of the actual ionization energy, low ionization energy means easy to remove. High ionization energy means harder to remove. So these would have a higher ionization energy. They'd be harder to remove than over on this side. Okay, sorry, let's clean this up because we're going to do another one. Okay, our last periodic trend is very similar to ionization energy, except for like the exact opposite, right? So ionization energy is the energy required to remove an electron. Electron affinity is our last periodic trend, and that's the energy that's released or gained when an electron is added to an atom, right? So if I take an electron away, I create a positively charged ion. If I add an electron, I'm going to create a negatively charged ion. Oh. So the periodic trends here are actually, they're the strongest from left to right. Again, this side of the periodic table, the right side, these elements, it's very easy to remove an electron from. Or I'm sorry, to add an electron to. They very much so want an extra electron. Over here, these electrons are these atoms are very hard to add an electron to. They really don't want an extra electron. If anything, they want to give it up. They don't want their electron that they have. They don't want to accept yet another one. Okay, so our trend for this one is going to go from left to right. There is a bit of, depending on the textbook that you look at, there's a bit of a downward trend as well, but we're going to say that it's really only the left to right trend that matters. Okay. And the other thing I want to point out is look at how the Nobel gases are an exception. That's part of what it means to be a noble gas, and we'll talk a little bit more about this in the next lecture, but they are perfectly happy the way that they are. They don't want to get rid of an electron, and they don't want to accept another electron. So this is the exception to our electron affinity trend. It increases as we go from left to right, as long as we ignore those noble gases. Okay. So again, we're going to take our periodic table and we're going to note that the increase in electron affinity occurs from left to right. Okay. So now let's do a few examples here. Lithium or oxygen, which one is going to have which one is it easier to add an electron to? So has a higher electron affinity. If you forget about what that corresponds to, remember affinity means to like something. So an electron affinity means that that atom really wants an electron. All right, so we're going to look at oxygen and lithium. Which one has a higher electron affinity? Is it easier to add an electron to? That's going to be oxygen. Aluminum and chlorine. Same sort of idea. You just got to find them on the periodic table. Aluminum, chlorine. Chlorine would have the higher electron affinity. And finally, sulfur and calcium. Because of the periodic trends, sulfur has a higher electron affinity. Sorry, my charger popped out.